Lesson 3 is the first of 2 lessons on ratio, and ratio is the second of 10 major concepts that we're covering in Shormann Algebra 2. We're introducing all of the 10 major concepts in the first quarter and building the foundation. So these lessons will have a little more rules, a little more definitions than the remainder of the course. Lectures will be a little bit longer, but for the most part, the practice sets will be easier because it's just basic information plus a lot of review. So here, starting out with ratio, think about this photograph here for a minute, and actually there's 2 photos there, one of the purple coneflower, another one of a dragonfly, and both of these have something in common. They have a numerical relationship referred to as the golden ratio or divine proportion. And that shows up in a lot of places in nature. That ratio does. From scale-like pattern on a dragonfly's wing to the spiraling pattern that you can see there on the head of those composite flowers called purple coneflowers. So maybe you can see that pattern there that kind of goes around and around. The Greek letter phi is often used, or Greek letters are often used to represent a particular number, like pi is for 3.14, phi is for the golden ratio. And we'll talk about that a little bit more during the lesson. But anyway, I thought it'd be good to just start by connecting ratio with nature, the study of math with the study of nature. Math is the language of science. So beginning with ratio, let's look at the history of ratio, and particularly the word ratio. And that word, ratio, it has its origins with the idea of rational or reasonable. I mean, you can see the prefix there, ratio, in rational. Rational thought, purposeful study. The Greek word for that is logos, and that also means word. So, for example, John 1:1, it says, "In the beginning was the Word, and the Word was with God, and the Word was God." So that in the original Greek is logos. In the beginning was the logos. So logos, it's also found in words like biology, so we see that suffix there, logi. Study of is what that means. Also consider the word logic. So when someone says that's logical, they mean that makes sense, or that sounds reasonable. So we can compare then John 1:1 to Proverbs 1:7, which says that the fear of the Lord is the beginning of knowledge, but fools, they despise wisdom and instruction. So what can we learn from all these verses? Well, if you reject logos, in other words, God's word, you're rejecting God. And that means you're rejecting reason, because reason is related to that word logos, and that makes you a fool in the end, no matter how smart you think you are right now. So please don't be a fool. Don't reject God and His Word. So man didn't create the idea of ratio. God gave us the idea of ratio. We discovered that, and that helps us understand His nature. Christians worship the one true God, who's also 3 persons, and that unity and diversity God displays is reflected everywhere in His creation. We can use the idea of ratio as a tool to study God's creation by comparing. That's what we're doing with a ratio, comparing one thing to another, comparing this to that. Ratios help us make sense of how one thing relates to another, including how the Creator relates to His creation. Of course, this idea of ratio in mathematics, we're comparing numbers, numerical amounts. So we could say the ratio of wings per dragonfly in that photo I showed earlier, that ratio is 4:1. Ratios are also written as fractions, so like 4/1 is another way to write that. So that word ratio, it has profound implications for understanding God's creative ways and understanding His Word, understanding His creation. It's super important in this course because it applies in one way or another to all of the 10 major topics covered in this course. We already had to use it in lesson 1 and 2, and that shows the interconnection between these 10 major concepts as well. It's hard to talk about them completely separately from each other. There's some integration that's necessary. So look at this, getting comfortable using ratio to compare one thing to another. That's perhaps the single most important idea that will help you do well in this course. So that the things we learn, they're not like separate, isolated events. that there's relationships between them. There's some interconnectedness, some integration between them. So when we think of ratio, think of fraction. So let's talk about fraction. That word, that comes from the Latin word meaning to break, and break apart from the whole. And we just talked about writing fractions as ratios. So 4/1 was our example there. So there's a significant connection between the two terms. So like I said earlier, when you think or when you hear the word ratio, think fraction. Fractions can be thought of as portions. And actually the word fract, that was first used in early Christian churches as a way to describe the breaking of bread during communion. And communion is described in 1 Corinthians 11. So during Holy Communion, or Eucharist it's also called, the bread is broken. Each participant receives a portion or fraction of the whole. Maybe for sanitary reasons during communion, your church gives out individual wafers instead of a whole piece of bread broken. But the whole piece of bread, that really better symbolizes the body of Christ, broken for our sins. So that receiving of an individual portions from a single piece, a whole, that is that idea of unity and diversity again, and is expressed everywhere in God's creation. Ratio is everywhere because God's hand is everywhere present, as he uses every way possible to turn us towards him, including mathematics. Let's go on now to part B on rational and irrational numbers, and that diagram there, that'll help you discern between the two major groups or sets of real numbers, which are the rational numbers and the irrational numbers. And you were introduced to most of these different number sets in lesson 1. So let's just think about them a little bit more here. Real numbers, so that's this entire group is what we're describing as real numbers. That's everything. That's the whole set of numbers. And it includes two major groups. One group that can be written as a fraction of integers, that's the rational numbers. And then the numbers that cannot be written that way, those are the irrational numbers. They can't be written as a fraction of integers. Now you may remember from your previous math course that any number, it can be written as a fraction by giving it a denominator of 1. And so 6, for example, we could make that into a fraction just by writing it over 1, 6/1. So we can say that equals 6. So hopefully you know that already. And that's why we can think of numbers like a 2, a 5, a 5,000, anything else. We can think of it as a rational number because we can always write it over 1. Decimal numbers are rational numbers too. So 1.24, for example, I can change that into a rational number. I can write it over 1 first, then I can multiply it above and below by 100. And that'll get rid of all the decimals, right? That just makes it 124 over 1 times 100 is 100. Now it's a ratio of integers, 124 over 100. Now irrational numbers, like pi, those can be written as decimal numbers. It's just that their decimal pattern never repeats. As far as we know anyways, that does not repeat. That's why they're called irrational numbers. We can't find a reasonable pattern that their decimals make. So the behavior of rational numbers, that's one of the great mysteries of mathematics. So remember, ratio, that word, that also means reasonable. So irrational, unreasonable. You think of unreasonable when you see that. So they defy human reason. We just can't fully understand, comprehend them, calculate them. And that should humbly direct our thoughts to God, who made these numbers, and he understands everything, including something that has an infinitely non-repeating decimal pattern. So we don't want to be like the Greeks, who ignored irrational numbers. They were afraid of them simply because they're too complex for us to fully understand. Is God all-knowing, or is he not? Can we trust him or not? I say yes to both of those questions, and that helps me put myself in my proper place of a human who wants to know more about God's creation and how it works so I can understand him better, but at the same time knowing that I'm not going to understand everything about his creation. So let's finish part B by looking at some special irrational numbers found in nature, and 3 of them in particular: phi, which we already talked about, pi, and then e. So note also that while any 2 numbers can be written as a ratio, that doesn't mean they are rational numbers. So for the 3 numbers below, the comparison of this to that results in an irrational number. So phi, that's the first one here, and that's also called the divine proportion or golden ratio, like we talked about before. And the famous Greek geometer Euclid, which we'll talk about when we cover geometry, he showed that phi can be found from a ratio of line segments, where you have a diagram like this, not exactly like this, but something similar to this, where this is A, we'll call this point C, and this B, and phi, that's equal to AC over CB, and it's also equal to AB over AC. And there's a certain spot where you can put C where this works out, but what ends up happening is this distance here of CB, it equals 1, and then AC, that distance, equals phi. Rounded, remember it's an irrational number, so we have to round it. It doesn't have a repeating pattern. It equals 1.618, rounded. So next one, pi, that's the ratio. It's actually another ratio of the circumference to the diameter of a circle. So you take the circumference of a perfect circle, divide it by its diameter, it's going to equal an irrational number. And that equals rounded 3.14. And that's the number we'll normally use for pi in this course. We'll use 3.14. Last one is E. And remember, Leonard Euler, he likes to use symbolic notation to shorten things up and make it simpler to write mathematics. So this is called the natural number, or also Euler's number, and rounded, that one equals 2.718. That's normally what we'll use in this course for E. Now, we'll talk about infinite series more later, but one way to estimate the value of E is to add values of this infinite series, where you have the first term of 1, and then the next one is plus 1 over 1, and then plus 1 over 1 times 2, and then plus 1 over 1 times 2 times 3, and then 1 over, I bet you can figure out what the next thing would be, and adding all those up, if you run that infinite series out long enough, you will get that 2.718 value. E has a lot of different applications, everything from calculating bacteria growth rates to calculating future values of a present sum of money put into a savings account. So it's a super useful number. We'll use it more later, and we'll also talk about infinite series more in Lesson 25 and elsewhere. Let's move on now to Part C on simplifying complex fractions. And here we're getting more into mathematically working with fractions. And we consider fractions to be complex fractions when either the numerator, the denominator, or both of them are fractions themselves. So to simplify them, you just turn them into a multiplication problem, and multiplying above and below by the reciprocal of the denominator fraction. So look at A, simplify that. And so what we're looking at there is this fraction, 1 over A, divided by this fraction. And maybe you remember, like from a pre-algebra course, maybe you remember thinking of 1 over A divided by. That's what the fraction symbol means, right? It means divided by. 1 over A divided by 1 over 4. Remember how you simplify something like that? Or perform the operation on it, you invert and multiply, right? You turn the 4 over 1 over, or 1 over 4, make it into a 4 over 1 and turn it into a multiplication. You say 1 over a times 4 over 1. That's equal to 1 times 4 is 4 over a times 1 is a. And that's the answer. So what we're going to do instead here, I mean, you can do it that way if you just really, really want to do it that way. But what we're going to do is do it like this. Leave it all as a fraction. And we're still doing like an invert and multiply, but we multiply the numerator fraction and the denominator fraction by the reciprocal. So we just say times 4 over 1 times 4 over 1. And so what that ends up doing is canceling everything out in the denominator. And in the numerator, we end up with 1 times 4 is 4 over a times 1 is a. Same thing as we got before, right? And then all of that is over, all that stuff that canceled on the bottom in red, that equals 1, right? So anything, including a fraction, anything over 1, we can just take that over 1 part out, right? It's understood that this is equal to 4 over a. We don't write it 4 over a over 1. So just like we got before, we get the same answer, right? 4 over a. B, we need to be careful with this. Look at it's x over y over 5. You see that between the y and the 5, the fraction bar is a little bit wider there. It's not much wider, but it is. And so we think of that as 5 over 1. And so we're doing x over y over 5 over 1. And so that means we need to invert 5 over 1, multiply above and below by 1 over 5. X over y over 5 over 1 times 1 over 5 times 1 over 5. So all that cancels in the denominator. Just that's always what's going to happen when we do this. And in the numerator we end up with x times 1 is x over y times 5. Normally we write the number first, so we'll say 5y instead of y5. So x over 5y. That's what that simplifies to. C, can you do that mentally? Can you take that 3 over 5 and just flip that and make it a 5 over 3? So you're going to end up with a times 5 is 5a over b times 3 is 3b. 5a over 3b. If you want, you can multiply above and below by 5 over 3. You can see all that cancel on the bottom, and there it is, 5a over 3b. Looking at D, kind of separate an area off to do D in. 7, we need to make that a 7 over 1. See, that fraction bar is a little bit bigger. It's the 1 over x plus y is the denominator fraction. So we say 7 over 1 over 1 over x plus y. So we've got a sum there, 1 over x plus y. That's okay. We could put that in parentheses, just kind of keep up with the sum there, and multiply above and below by x plus y over 1. Multiply above and below by that x plus y over 1. And all of that's going to cancel on the bottom. And so we get 7 times x plus y over 1 times 1 is just 1. And so we can simplify that even more, because anything over 1 is just what that numerator is, 7 times x plus y. We could also have written that 7x plus 7y, but we'll just leave it in a factored form like that. When you do these problems in the practice set, sometimes the parentheses will be around the fraction part, so since it is kind of hard to tell that this fraction bar is a little bit bigger than the one below it, and so that's like the main big fraction, we'll have these parts in parentheses so that you know clearly, oh, that 1 over x plus y is the denominator fraction, so I need to change the 7 to a 7 over 1. And you don't have to be so observant, I guess you could say, about how wide that fraction bar is, since there's hardly any difference. Moving on to D, let's look at fractions and square roots. And there's going to be times when you're working an algebra problem and you get a fraction inside a square root. So that's a special situation. The normal or standard form is to apply the quotient of square roots rule, followed by getting rid of the square root in the denominator. So we want to get rid of that square root in the denominator. So let's look at A. What are we doing to simplify that? Well, first we want to use the quotient of square roots rule and say square root of 3 over square root of 2. Now we want to get rid of that square root of 2 in the denominator, and we do that by multiplying above and below by the square root of 2, which is the same thing as multiplying by 1, right? Expand that out now though. Square root of 3 times square root of 2 is square root of 6. Square root of 2 times square root of 2 in the denominator, that's 2. So now we have square root of 6 over 2. That is the simplified form of A. That's the standard form. It's not like having square root of 3 over 2 is bad or something. It's just not the standard form. So we want to put it in standard form. Look at B. Using the quotient of square roots rule again, we'll just say square root of 3 over the square root of 4. Well, the square root of 4 is 2, right? So we don't need to multiply above and below by the square root of 4 here. We'll just say square root of 3 over 2. And that's it. C, we have 5 over the square root of 5. That's not standard form. We want to get rid of that square root in the denominator, so we multiply above and below by itself by the square root of 5. And so then we end up with 5 times the square root of 5 in the numerator over square root of 5 times square root of 5 is 5. And so those cancel though, right? 5 over 5, that cancels. And it's understood there's a 5 times 1 in the denominator, right? So that square root of 5 over 1 is equal to square root 5. Right, just to be clear here, it's understood we could always write that as times 1. Anything we can write it as times 1. We just do that for a simplification purpose. We don't write it every single time, the ones. Okay, and then D, being careful here, we have an x over y over the square root of 2, and let's make that a fraction, over 1. So we're multiplying above and below by 1 over square root of 2 to simplify this. Okay, so all of this is going to cancel. Now we have x over square root of 2y. Now that's not standard form, so we want to multiply above and below by square root 2. And so that, let's just put the answer up here. It's going to be square root of 2x over square root of 2 times square root of 2 is 2y. So in dealing with fractions and square roots, it's not standard form to have a square root have a radical sign in the denominator. We get rid of that by multiplying above and below by whatever that square root of the denominator is. Now let's go on to part E on logarithms, and Shormann Algebra 1 students, this is a review for you. And if you didn't use Shormann Algebra 1, this may be new, so just be careful, pay attention. And as we mentioned in lesson 2 though, this is what you need to think about. Logarithm means exponent. Remembering that connection between logarithms and exponents, that's the single most important thing for really understanding and easily understanding logarithms. Originally though, logarithm was Greek for the word number of ratios. So that's why we're studying this in ratio, that's what it used to mean, is ratio number. And John Napier, a Christian man, he invented logarithms around 1614. He had many talents. He was a part-time astronomer. He saw the need to simplify the process of working with really large and really small numbers. So exponents, they weren't really developed till 1637, so his original form, Napier's original form of logarithms, doesn't look anything like we describe them today. The form we use now looks more like Leonhard Euler, how he described him in Elements of Algebra. That was his book he wrote in 1765, and that modern algebra courses originate from and are based off of, including this course as well. So in Euler's day, logarithms were found by referencing tables printed in the back of mathematics textbooks, like these long page after page after page tables. Today, though, those tables are stored in a calculator. So this is a subject that a lot of times you can use a calculator to find the logarithm of something. So you need a calculator that has buttons on it that say log or ln for natural logarithm. We'll talk about what those mean more as we go on. And we talked about Johannes Kepler. This is the third lesson we've talked about him. He's one of the first scientists to use Napier's logarithms, and much of his work revealed to people the real universe God had made, as opposed to the false and superstitious world created by astrology. Big difference between astronomy and astrology, and there's still problems with astronomy, especially some of the ages that they come up with. Men like Kepler, they called to God in prayer. He answered. He taught them great and unsearchable things that no one before them had known. That's what Jeremiah 33:3 says, is to call to him and he will answer, teach us great and unsearchable things that we didn't know. If God led these men to discover new things, he can certainly lead you through this course if you ask, and discover new things for yourself, and maybe later on you'll discover some really new original scientific or engineering principles. For now though, let's review some of the concepts of logarithms you learned in Shormann Algebra 1. So look at example 3.3. This is about logarithms without a calculator. We're not using a calculator right now. Just apply the logarithm rules, and those are in your rules section for this lesson. So if there's any of those that you should write down, then write down the logarithm rule about if n is equal to b to the L power, then log base b of n is equal to the exponent L. Remember, logarithm means exponent. Okay? So log 2 of 8. What does that mean? Well, thinking of log b n equals L. Log base 2 8 is equal to L. We're solving for L. So just rearranging here, n is 8 and the b is 2. So in the n equals b to the L relationship, in the exponent relationship, we would say that 8 is equal to 2 to the L. And these aren't designed to be some weird decimal number. I mean, just think about it. 2 to the what equals 8? Well, 2 cubed equals 8, right? 2 times 2 times 2. So L is 3. Okay? Logarithm means exponent. Saying, what is the logarithm of 8? So what is its exponent when the base is 2 for that particular problem? Well, its exponent is 3. Logarithm means exponent. Look at b. Log base 10 of 1,000. So here we have log base b, where b is 10 of 1,000. So here we're going to say log base 10 of 1,000 equals exponent, equals L. Rearrange that. N is 1,000, so 1,000 is equal to the base of 10 to the L power. So L is the exponent. What is the exponent here? Well, 10 to the what equals 1,000? Well, 10 times 10 is 100, times another 10 is 1,000. So it's 3. Again, it equals 10 to the third. So the answer is 3. L equals 3. Well, that's the same answer as A. Well, that's okay. It's just the exponent, right? It's a different base now. 10 to the third equals 1,000. 2 to the third equals 8. Let's do another one. Let's do C. And here we have log base 4 of 16. So think about logarithm means exponent. We're saying that that argument, that's what we call the big number, the log of, whatever we're taking the logarithm of, that's the argument. 16 is equal to the base of 4 to the L power. Well, 4 squared equals 16, right? Now, 2 to the 4th equals 16 as well, but we want the same base, right? We don't say, well, 2 to the 4th and the answer is L equals 4. Well, no, we want the same base. We wouldn't put a 5 here or 2 or 7. We put the base of 4. 4 to the L equals 4 squared. So L is equal to 2. The logarithm of 16 with a base of 4 is 2. And then D, 27, the argument, is equal to 3 to the L. Well, 3 cubed equals 27, right? So L is equal to 3 for that one. So I was showing a little less work as we went on there, but for all of those, if you remember, N equals B to the L, and log base B of N is equal to L. When you're given this much right here, basically, log base 2 of 8, log base 10 of 1,000, log base 4 of 16, log base 3 of 27, they're asking you to take that and find the exponent, find L. That's what they're asking you to do. Here's another example, 3.4, another logarithm without a calculator. Find A, B, and C in the following table. Okay, so here's A, here's B, here's C. Figure out what those are. So we have log base 10. So let's just look at the pattern here. Look at the pattern over here. It goes from 10,000 to 1,000. It's going down by a factor of 10 every time. So look at the corresponding pattern in the log base 10. So remember logarithm, that means exponent, right? So log base 10 of N, so this first one, that would be log base 10 of 10,000, because N is 10,000. So how many zeros do you see there in 10,000? Well, there's 4 of them, right? What is the exponent equal? What is log base 10 of 10,000? Well, it equals 4. So this is something that happens with base 10 logs. Log of 10,000 has 4 zeros, the exponent is 4. Because you're multiplying 10 4 times, right? So we have 4 blank 2 1. Go back up. 1 2 3. 1,000. Log base 10 of 1,000 is 3. We just did that in example 3.3, right? So A is equal to 3. So we have 3 2 1 0 minus 1. So we're just going by integers, right? Skipping along there. So B is equal to 0. Log base 10 of 1 is equal to 0, right? Because that means 10 to the exponent of 0. 10 to the 0 is 1, right? Anything raised to the power of 0 is 1. So that makes sense. And so we just keep going here. Minus 1, minus 2, minus 3, minus 4. So C is minus 2. So that's saying that log base 10 of 0.01, which is 1/100th, right? That's equal to minus 2. Look at the opposites here. So we have log base 10 of 100, that equals positive 2. Of 1/100, that equals minus 2. So you can kind of see that pattern as well there. Okay, last example, 3.5. This one's logarithms with a calculator. So get your calculator out. It needs to be a scientific calculator, and either one on your computer or a handheld calculator. Find each of these. So on your calculator, if you see the log button, it's understood that that is log base 10. And then if you see the LN button, it's understood that that is log base E, the 2.718 number that we talked about earlier. So look at this graphing calculator on an Apple computer, and you can see that it has an ln button for that natural log, the log base e, and then it has a log base 10 or just log button. So depending on the calculator, log base 10, it may just have log on it, and log base e, it'll usually just have an ln for natural logarithm. Notice there's no log base 2, log base 5, log base 7, log base 11, all of those. The reason for that is because log base 10, log base e, those are the two most often used types of logarithms. So these example problems are designed to help you discern between should I press the log button or press the ln button on the calculator. And that's really all you're doing on these. Is you don't have to know a whole bunch about logarithm, means, exponent, and all of that. It's just about pressing the right buttons on the calculator. Example 3.4 was more about understanding what logarithm means. So looking at A, what you would do is you would type in 500 and then you would hit log base 10. And the example says to write the answers to 2 decimal places. So this one is 2.69897, so that would round to 2.70. So we'll just say A is 2.70. Now let's clear that and let's just do that again. Notice what I did. I typed in 500 first, then I hit the log button. Now on a graphing calculator, if you're using a graphing calculator, a lot of times what you do on those is you press the log button first, then you type in the number, then you hit enter. And so it just depends on the type of calculator that you have. You need to get your user's manual out for your calculator if you're not sure what to do, if it's just not working. But either way, whether it's a graphing calculator, no matter what type of calculator, you should get rounded to 2 decimal places 2.70 for that result. Now for B, we want to do natural log of 500. So let's clear that, type in 500 again, but this time we're going to press ln. And so we get 6.21 for an answer there. And so B is 6.21. So think about what we're doing here. Logarithm means exponent. What we're saying is in A, we're saying that 10 to the 2.70 power, or about that, we rounded that, that should equal about 500. And then E, so that means 2.718 to the 6.21 power, that should equal about 500 as well. It's not going to exactly equal it because we rounded things, but it should be pretty close to that. So look, we could type in 2.70 and then we could hit this 10 to the x button, which means that we're saying 10 to the 2.7. What do we get? Right about 500, right? 501.2. If you understand that logarithm means exponent, this is a good way to check your work on problems like this. We could do it for B as well. Base E is 2.718. We hit this XY button, so that means 2.718 to the 6.21. Hit enter, almost 500 again. But we rounded that stuff, so that's why it's not exactly 500. But that gives us confidence that we did the problem correctly. Let's clear the calculator and go on to C, log of 0.068. So we just do 0.068, hit the log base 10 button. We get a negative number this time, but that's okay. That's what it's supposed to be. Minus 1.17 is the result there. So we'll say C is minus 1.17. Clear that, and let's do D, natural log of 0.068. So we do 0.068 natural log minus 2.69. So D is minus 2.69. Remember, logarithms are designed to work with really big and really small numbers, much bigger than 500, much smaller than 0.068. It doesn't really save us anything to write 500 as 2.70 in A as its base 10 exponent of 2.70. I mean, we're still using the same number of digits, and we even have to add a decimal point in, so it doesn't save us anything. But what if it was log of 10 billion or something like that? Instead of writing 10 with a bunch of zeros after it, then that would be easier to write the logarithm of 10 billion. So just remember, we use logarithm to work with really big, really small numbers. Logarithm means exponent for whatever base that we're working with, whether that's base e, base 10, base 2, just whichever one it is. Okay, well that's all for lesson 3.